Hi, everyone. This is Ashok Kumar, and I have my colleague Barthold, who is going to do the presentation today on how we did the Prestesmo, which is Presto 2.0 benchmarking inside IBM. And we are going to also show the results of Prestesmo and the query optimizer that we found when we were doing the 100 terabyte benchmarking. Going to the next slide. So in today's agenda, we have what's the next.data, which is basically a platform where you can have a multiple SQL engine running, Presto, Prestesmo, Spark, and others. And this is what we used as software for running the benchmarking. Presto engine, we all know it's a Java engine. And then we have the Prestesmo, which is also called Presto 2.0, C++ engine that we use for the benchmarking. Then we have the query optimizer, which supports multiple engines, and it do the rewrite, do the runtime optimization, stuff like that, which my colleague Barthold is going to explain later in the session. Then we have the IBM Fusion HCI, and we'll explain what it is. And then at the end of the session, we will discuss 100 terabyte benchmarking, how we did it, show you some of the results, and then we can open up for question and answer. So moving on to the next slide. So in the Presto architecture, we know that we have the coordinator and the worker setup, where we see on the coordinator the query comes, there's a parser, there is an optimizer, there's a scheduler, and from there we have a connection to the Hive meta store. From the scheduler, it gets sent to all the Java worker, and then the results get executed on the worker, then it gets sent back to the coordinator, and then it goes back to the client. So this is also the MPP architecture that we call. It's a highly scalable. Performance-wise, it is great, and it cuts it gives you the good result if you are really not into the performance specific. But if you really want to have an engine running on the performance, where performance is the main factor, then we really suggest to go to the Prestesmo, which is on the next slide, that we see the architecture where all the Java worker, we know it's being replaced by the CPP worker. Then we have the vlogs library, which is the accelerant, and then it has the runtime optimization. We have the smart IO prefetching and caching. We also have the memory arbitration, where we get the spilling feature as well. So when we did it on the what's the next.data, that's where we have the Prestesmo. And moving on to the next slide, I can explain that we have the open source engine, Prestesmo, which is based off of version 2.86. And on top of that, we added a few changes of our own to improve the memory management and to also improve the stability. While we were running the benchmarking, we saw that the pods were crashing. So we wanted to see what's going on. We looked into it. We found that it was the memory that was being hit. And once you hit the limit, it was crashing the pod. So we looked into it and found that there's a way we could improve it. And we found that the cache shrinkage, if we can work through that, the API was there. So we worked in the IBM side, and we started doing the periodic cache shrinkage, and that really helped us with cleaning up the memory, freeing it up, and that helped with not hitting the out of memory users, out of memory error, as well as it helps with all the optimization there as well. This fix, which was internal to IBM, it's also being improved further. And rather than periodically reclaiming the memory from cache, we are also making it conditional to make it better than the periodic. So that work is still in progress, and the research is also being done. And I think moving on to the next slide. So this is where I think my colleague Bartol will take it over, and he is going to walk us through the quick view of what this 100 terabyte TPCDS look like, and then we will go into the other details that we have in our agenda. So thank you, everyone. Bartol, over to you.
So we ran Presto 2.0 on a 100 terabytes TPCDS benchmark. Just to refresh everyone's memory, there's 24 tables with 7 fact tables and benchmark model sales and sales returns for 3 channels, store, catalog, and web. And the inventory table is for the catalog and the web sales channels. And just to give you an idea of the size of the tables, the store sales table has 288 billion rows in it. Catalog has about half of it, and web another half of that. And the model says that with regards to returns, store sales returns is about 10%, 28 billion rows, and catalog and web returns accordingly half of it again. There are 103 very challenging queries in it, and queries are very diverse. They range from very large fact-to-fact joins, meaning store sales with store returns, including across all the 3 different channels. But there's also small joins with the dimension tables, of course. There are large aggregations and sort operations in the queries, and there's definitely a high sequential I/O throughput required as well. And the queries have multiple snowflakes. So we're going to report on the power run here. And the focus was on testing out the Prestissimo 2.0 that Ashok explained. But in order to stress this Presto 2.0 better and makes queries more executable, we introduced an additional optimizer on top of the Presto optimizer or compiler, which we call WXD Query Optimizer. And it goes along the line what Tim says this morning about disaggregated components. You can think of that as a disaggregated optimization, where you have a query optimizer that does high-level optimization, things like redundant scan elimination, decorrelation of queries, or determining the correct join order. And the Presto optimizer then does a low-level optimization, as it is much more familiar with the physical cluster layout and the data layout. Hence, it creates the different stages. It places exchange operators. It decides on the join methods, whether it's a broadcast join or a partition hash join. So this is a disaggregated optimization model here, and another reason why we do that at IBM is because we are doing multi-engine lake houses, which means our optimizations do not just apply to Presto 2.0, but also to Java, Presto, Spark, and maybe others in the future. Just to give you a quick rundown, the Presto server here that takes in the Presto SQL query. We have created a plugin that sends the query to the query optimizer that has no data, but also schema information, the statistics, as well as the constraints information that we pull from HMS, the Hive Meter Store that we are using in our setup. The query optimizer then goes through the query graph model, applies all the different rewrite rules, and does the costing using the optimizer, and creates an optimized query that is being sent back to the Presto optimizer, which does its job the way I explained it before. Here in the diagram, you only see submitting the queries against Presto 2.0, but as I said before, multi-engine, it can run against other runtimes as well. In terms of experimentation, we did it on an IBM Fusion HCI box, which is a hyper-converged system with NVMEs. It comes obviously in different form factors. We had chosen a form factor of compute nodes with 11 nodes. Each of one has 64 cores in it, and we use 2 terabytes of RAM per node. It also has GPUs in it, but most importantly, it has a dedicated storage network. And per pod, we get about 25 giga GBE for the different pods. It has OpenShift on it. which allows you for very rapid deployment, putting your OpenShift applications on it. It provides high performance as it is a bare metal OpenShift, which eliminates the hypervisor overhead, and it has a built-in S3 endpoint over a scale-out parallel file system. And it comes in different small factors. It's very expandable, so you can start off with 4 nodes, increase it to 7 nodes, expand it to 11 nodes, or expand it to 18 nodes, or go across different racks. So given that hardware, we put Presto 2.0 on top of it. We had chosen a part for the coordinator. We placed all our different workers, and we connect to the S3 endpoint, which is the Red Hat multi-cloud object gateway, which is Nuber, and that one runs over NSF, which is the namespace file system. In terms of object layout, I don't want to go into too much detail here, but we have chosen fairly large row groups for more efficient I/O, and we maxed out the placement of the pods in order to get best CPU and memory utilization. In terms of setup, we have only chosen one coordinator, and we have 75 pods. Per pod, we have one Prestissimo worker. We have 13.3 cores per pod, which brings us roughly to around 1,000 cores total for the benchmarking work. There's a couple of information about properties. As you know, Presto 2.0 and Presto in general is very configurable in terms of properties. Definitely you want to max out the task concurrency. We have exploited what Velox provides with the adaptive partial aggregation, which is beneficial. In terms of execution policy, we had chosen the phased execution policy for now, but we may change it going forward to use a grouped execution policy. In terms of scheduling, we increased the max split per node, but also the pending split per task. And we maxed out as max HTTP requests per queued per the destinations. Optimizations, we do prefer partial early aggregation in the Presto compiler, and we also enabled rewrites such as predicates, in-list predicates as inner joins. The last one is very important. As Ashok pointed out, we turned on the async data cache, and maybe I'll show you a few numbers, how that was beneficial. This one is the 103 queries, and the major takeaway of that one is the orange, which is without Presto 2.0 and Query Optimizer. You can see that several queries, they just go through the roof, literally. So we capped them off at some point in time to just make it more presentable here. But as we did the tuning with the optimizer as well as Presto 2.0, some of those queries move as heavy hitter queries before into the long tail. Okay, they are not heavy hitter queries anymore. And as you can see at the front of the diagram, for the heavy hitter queries, several of them we provide multiple X improvements in terms of execution time. Okay. Here's the overall breakdown. Going from Presto to Presto 2.0, we measured a 2.6x improvement, and then turning on the high-level optimization, we see another 3.2x improvement, and turning on the async data cache, again, we see a 1.2x. So the whole thing translates roughly into an order of magnitude. Memory footprint is very important. We only did the power run, but for multi-streams, that will become very important. And as you can see, the average peak memory footprint across all the queries is being improved by a factor of 3.5x, thanks to Presto 2.0. And if we take a look at the peak memory footprint, that one also dropped by a factor of 2.1. So roughly to summarize, tremendous progress have been made with the open source Prestissimo in terms of scale out. We demonstrated running TPCDS 100 terabytes. We used 75 workers, but we also experimented with 100 plus workers. It definitely scales out. It is stable and it works very efficiently, and the memory management definitely improved significantly compared to prior versions. And I think we have proven that Prestissimo can efficiently run 100 terabytes TPCDS benchmark. Thank you.
Okay, thank you everyone. If you have any questions, just do post it there. We will try to answer them all.